Hi, and welcome to our 9 a.m. press conference, New Research on the Ionosphere, Our Interface to Space. Our participants today are Bob Robinson from the NASA Goddard Space Flight Center and Catholic University of America, Dolores Knipp from the University of Colorado Boulder, and Scott England from the University of California, Berkeley.
Good morning. So thank you for coming by to hear about the ionosphere. The ionosphere is the region of Earth's atmosphere that separates the space environment from where weather takes place, the lower atmosphere where weather occurs. So we'll be presenting new research that's really changing our view of the ionosphere, and it really does underscore the importance of understanding the ionosphere because it's a highly variable regime that's very important for a variety of reasons. We're also going to be describing two upcoming NASA missions whose goal is to enable unprecedented studies of this poorly understood region of space. So the boundary between outer space and the lower atmosphere where weather takes place isn't really clear-cut. It's an area that displays properties of both the lower atmosphere and space. We call it Earth's suburbs. It has a combination of the urban characteristics of the city and the rural characteristics of places where the population is much, much less. So this boundary, as you can see in this image, is between about 80 kilometers altitude, and it goes up to about 1,000 kilometers. So it's a very extended region of ionized plasma in the atmosphere. And it's important because the ionosphere is where radio communication signals pass through. The signals that make our navigation systems pass through the ionosphere. This is where many of our satellites orbit, and also the International Space Station orbits through the ionosphere. Plus, it's the location where electrical currents flow, and these electrical currents can have effects on our power grid on Earth. So we'd like to understand the ionosphere well enough to anticipate all the complex changes that could take place, especially in association with a large solar storm. So the challenge is that there's many competing processes that influence the ionosphere. It changes from day to night, changes in response to a myriad of other inputs from the sun, from the Earth, and even from the chemistry of the atmosphere itself. So we want to understand what drives those changes, because that variability can affect our radio communication signals, our navigation systems, the orbits of satellites, and the voltages on our power grid. So today we'll be highlighting new research that's really changing our traditional view of how the ionosphere works. And I'm going to begin by describing the results of a study focused on how energy enters the ionosphere from above. Energy from above occurs primarily during large magnetic storms caused by solar flares and coronal mass ejections. So disturbances on the sun, such as the coronal mass ejection you can see in this animation, produces energetic particles that travel through space in the solar wind. They strike the magnetosphere, and ultimately they end up in the ionosphere. We've known for a long time that the energy from the solar wind deposits energy into the atmosphere, but the mechanisms for that transfer of energy are not really clear or well understood. So traditionally, we've thought that the transfer is totally driven by variations in the solar wind itself that appear in the manifestation of aurora and other effects in the ionosphere. And different inputs in the solar wind produce different effects down in the ionosphere. But our research is showing that this is only a part of the picture. If you notice from this animation that it shows something strange happening far down in what we call the tail of the magnetosphere. And as a result of that interaction, particles stream toward the Earth and impact the Earth sort of uniformly around this ring that we call the auroral zone. But what we're finding is that there's localized processes that are important to determining how that transfer of energy takes place and ends up in the ionosphere. And the new view has been enabled by our ability to track on a global basis what's happening. And we do this using a set of observations from a global constellation of satellites called Iridium. And you're probably familiar with Iridium as the communication satellites. They're also producing data that's very important scientifically, and we've been able to use those to map the energy flow into the ionosphere. And it turns out that the process is very similar in the way that lightning forms and discharges during thunderstorms. Lightning occurs when electric charges build up in clouds. This results in a voltage difference between the cloud and the ground, or from one cloud to the other. But for lightning to strike, there has to be an electrically conducting pathway between the cloud and the ground, or between two clouds. And once that happens, this electrical energy discharges, creating the lightning stroke and releasing all this stored energy at once. So in much the same way, electrical energy caused by the solar wind striking the magnetosphere produces a voltage difference between different regions within the magnetosphere. So how does that get discharged? It gets discharged along the Earth's magnetic field lines where currents occur. And these currents are shown in this figure. They enter the ionosphere, but they can only close in the ionosphere if there's a conducting pathway, if the ionosphere is electrically conducting, so that these field-aligned currents can flow through the ionosphere. And what we've found in looking at the data from this global constellation of satellites is that the field-aligned currents themselves create the conducting pathway in the ionosphere to close the currents. So in other words, the currents enhance the conductivity in the ionosphere, allowing more current to flow, which allows more current to flow in the ionosphere. And that process continues until there is an explosive, rapid discharge of electrical energy into the ionosphere. And this rapid discharge of energy is very analogous to the way lightning is produced. Of course, the process is not exactly the same as terrestrial lightning. When I say it's a rapid transfer of energy, it takes place over maybe tens of minutes or hours, which is short compared to the time of a solar storm, which can take several days. Lightning takes milliseconds. But the amount of energy in one of these discharges in the ionosphere, it's actually hundreds of times more than the energy in a lightning stroke. So what these observations demonstrate is that the ionosphere itself is playing an important role in modulating the discharge of magnetospheric energy into the ionosphere. So it's the solar wind that determines the total amount of energy that's available, but then it's the ionosphere that's sort of modulating the rate and the location at which that energy is entering the ionosphere. So the data from the Iridium satellite constellation has allowed us to map this energy transfer in space and time. So here we show the energy being deposited into the ionosphere during a magnetic storm over about a 15-hour period. And you can see these intensifications as they occur rapidly in space and time. So you have to imagine that you're flying above a storm system, and you're looking down, seeing where the lightning, the random locations that lightning occurs. This is very much like what we're seeing in these data, in the time, temporal and spatial behavior of these intense energy deposition events in the ionosphere. So these discharges of energy, the magnetosphere ionosphere lightning, we call it, produces dramatic effects on the ionosphere. It's associated with, but not exactly coincident with, where the aurora occurs. It's associated with intense currents in the ionosphere, and it's associated with heating, much like lightning causes something to catch fire if it hits it. So all of these have important effects on the chemistry and dynamics of the ionosphere, and this new view of this energy transfer is giving us a much better understanding of what causes the dramatic changes in the ionosphere. And that'll allow us eventually to make predictions about the possible impacts on communication systems, navigation systems, power systems, but also on how it impacts our satellite orbits. And that's what our next speaker, Dr. Dolores Knipp, will be talking about. Thank you.
I'll let you keep this image in mind as I move forward. So hold on to that image, hold that thought. And as Bob has just mentioned, when there are disturbances in the magnetosphere, very often driven by storms from the sun, that energy can sweep from the magnetosphere down into Earth's upper atmosphere. He mentioned the word ionosphere, which is the charged part of the upper atmosphere, but that's encased in an envelope of neutral atmosphere, which is just the grand extension of the air that we breathe down here. What is amazing is that that atmosphere, because it is so tenuous, has the ability to respond and expand, and that influences satellite drag. And what that means is we may not be able to know when we want to know exactly where satellites are. So it's a prime business of Department of Defense, but also of great concern to NASA, to know how to forecast satellite drag and the positions of satellites. So my research is closely tied to what Bob talks about, but it does focus on the neutral part of the atmosphere, the thermosphere, which is that place where the majority of our satellites still operate. There's a huge fleet out in geosynchronous, obviously, but there is a large portion of our endeavor, our space endeavor is there, and of course the International Space Station is there. So we want to be able to help operators ultimately to figure out what's going to be where, when, and what is the possibility of a collision, and how might we avoid that. So we do not have a perfect set of observations for doing this, and we don't have a perfect set of models. And one of the things that I have been investigating on the behest of Department of Defense is, why do some forecasts go bad? And we have found the answer, and it is actually associated with that image that Bob just showed you. So when a geomagnetic storm hits, tremendous energy enters the Earth system, and it gets transferred into the atmosphere. That energy, the bulk of the energy actually comes from the sun, but during great disturbances called geomagnetic storms, that energy focuses into the auroral zone, just like Bob showed you and just like this image shows you. That extra energy causes the atmosphere, the molecules in the atmosphere, to fight for more room. And the only option they have is to expand upward. And that's a long-known interaction chain that's been followed for quite a while. What I like to tell my students is when the atmosphere heats up, it heaves up, which generates quite an image for them. It sticks in their mind anyway. But what this means is this swelling of the atmosphere, there's more stuff for our low Earth orbit or even medium Earth orbit satellites to run into. Ultimately, over time, it changes their orbital paths, and it changes our ability, if it's happening very rapidly, to predict how those orbital paths are going to change. So we've essentially got this system that's acting like a balloon, kind of puffing up and putting stuff in the way of our satellites. Ultimately, satellites in low Earth orbit deorbit, and you've probably heard some pretty spectacular stories about things coming crashing in, and how are we going to be able to predict that. What we have found out is that there is a trace chemical in the upper atmosphere. This has been known for a long time, but this trace chemical is called nitric oxide, and it is the cooling agent of the atmosphere. When you think about, we've talked about the energy coming in, we've got to get the energy back out somewhere, otherwise our atmosphere blows up, and that doesn't happen on a grand scale. So we've known for a long time that nitric oxide was the primary culprit in cooling the atmosphere and allowing things to settle down. So this is an image provided by NASA Langley, Marty Malinczak, who has been working with the timed SABRE instrument, and it shows during a great storm where the cooling is going on. And you go, gosh, that looks where the heating is going on, which is kind of confusing. You realize that the atmosphere is heating and cooling at the same time. Well, that's always happening, but in some storms, the system goes a little wild, and it starts cooling rapidly even while the heating is taking place. We've suspected that for a few years. I got onto this because I investigated a great storm from 1967 that I know had impacts on Department of Defense ability to track their satellites. And I saw an amazing graphic that came out in 1970, and as I was doing this research, I go, aha, I know what's happening. The system heated up very rapidly, but cooled down even more rapidly, and the models couldn't keep up with that. So what we have found by studying over 200 storms in a technique that essentially stacks storms up at their same kind of generic starting point, we have found out that events that come from the sun very fast, they're called shocked storms. It's like a shock that you hear with a supersonic aircraft. Those events create more nitric oxide much faster, and even while the forecasts think that the atmosphere is going to expand, it's starting to contract. We find out that does not happen, or at least not to the same degree, with the non-shocked events. And that is the new result that is just now coming into press. The paper is about to be accepted. That is actually rather, I would say it's stunning, but it's not. We know that the shocked storms have always created more havoc in the magnetosphere, and now we're finding out that it creates unanticipated difficulties with forecasting way down in the atmosphere where we have our satellite fleet. So here's this storm time breathing of the atmosphere. It actually does show expansion and then very quick contraction, and this is what we need to focus on now that we understand what is going on. How does this happen? How global is that cooling distributed? You saw that it looked like it was distributed in the same area as the auroral zones, and it is, but it gets transported out and has a very global effect. So with that, I will tell you that Scott is going to come up and chat with you about what's next. We've been using older data, but now new data sets are going to come online.
All right, thanks, Dolores. Okay, so Bob and Dolores have talked about how the ionosphere and the upper atmosphere respond to energy inputs coming in from outside of the Earth, be they charged particles or geomagnetic storms. And I'm going to switch gears and talk about two new NASA missions, which are both launching in the next year. And they're focused on looking at the link between the upper atmosphere and ionosphere and a different energy source, and that's actually Earth's weather systems that are happening down here near the ground. So Bob started off showing us the ionosphere at high latitudes near the poles, where energetic particles are able to come in from space and hit the upper atmosphere, create the aurora, and create the ionosphere in those regions. But over the rest of the globe, the Earth's magnetic field actually shields us from those particles. But above us right now, there is ionosphere, and that's actually created by sunlight. So we know if we go outside here right now, we're protected from harmful ultraviolet in sunlight by the ozone layer, which is above us in the stratosphere. The Earth's upper atmosphere is actually above that ozone layer, so it receives the full force of all the ultraviolet in the sun's rays. And what that ultraviolet does at these altitudes is it actually breaks apart the molecules of gas that we have here in the room, and it forms ions, it excites those, it ionizes them, and creates the ionosphere. And so our traditional view, if you look in textbooks about the ionosphere above us right now, is that it's really controlled by that ultraviolet in sunlight. And for sure, if we see a change in that ultraviolet, like during a solar flare, we see a change in the ionosphere. But I think one of the most exciting results that came out of NASA's timed mission that Dolores introduced us to is that the ionosphere above us also responds to Earth's weather systems happening right here near the ground. So there's this connection all the way from the ground out to hundreds of miles above us, where we think of it more as the inner edge of space, or this transition between to the suburbs, as Bob talked about. Okay. So how are we going to make these observations? I like this photo, so I'm going to talk about this photo. This is not a false color image or anything. This is a regular photo taken with a Nikon camera that you can go buy downtown, but it's taken from the International Space Station. So the astronauts take cameras up and they just set it to a long exposure and take a photo out the side. And you can see the Earth at night and pick out some cities in the Mediterranean. And you can see the lower levels of the atmosphere. And then when we get into the upper atmosphere and ionosphere, you can see this pronounced red glow, and there's a green glow at lower altitude. This is not aurora. This is over the Mediterranean. This is something we call air glow. And this air glow would be visible to our eyes if they were a little more sensitive. It's really red and green, and there's other colors in the infrared and ultraviolet. And those different wavelengths give us different pieces of information about what's going on. But the air glow is formed as a byproduct of that ultraviolet light that's energizing and ionizing the gas above us. And the two new NASA missions are both going to focus on studying this air glow as a way of seeing what's really happening. So here's the first of these two missions. It's called the Ionospheric Connection Explorer, or ICON. It's in low Earth orbit, which is a similar kind of orbit to the International Space Station, so the view out the side is going to be a little bit like that. And it's making observations in a few wavelengths of the air glow. So by looking at the infrared, we're able to look at that energy coming up from weather systems in the lower atmosphere by measuring the temperature response and the fluctuations. Then we can see how the upper atmosphere is responding to that by measuring wind. We do that by actually looking at that red and green light that we saw in the previous photo and looking at Doppler shift, so it gets shifted to the red or the blue end of the spectrum. This is the same technique astronomers use to look at stars and see how they're moving relative to the Earth. And then by making measurements in the ultraviolet, we can pull out the composition and the density of the ionosphere in this region. And this ultraviolet's really powerful, but it's a measurement we can only make from space, because the Earth's atmosphere and the ozone layer would absorb this if we tried to measure this from the ground. So we can only get access to this ultraviolet air glow by being up in space. The second of these two missions is called GOLD, and that's focusing just on that ultraviolet. GOLD's observations are taken from geostationary orbits. The view is a bit like what we'd expect from a weather satellite, so it remains fixed relative to a point on the ground. And by making extremely precise measurements in the ultraviolet, they're able to pull out measurements of the upper atmosphere and ionosphere. But I think something really exciting is the fact that we have both of these two missions launching in the same year, and we're going to be able to use data from both of them at the same time. So what we're seeing here in this movie, this is GOLD's view of the Earth. The colors that are appearing, this is the ionosphere. And you can see how ICON, which is embedded in the ionosphere, is orbiting the Earth and so is coming through GOLD's field of view. And you can kind of think of how we'll combine these two as how we might study a hurricane. So we might want a geostationary weather satellite to track that hurricane coming across the Atlantic, and that's the image that GOLD is giving us. But we might also want to get some other measurements that we can't get that way. So we might fly an aircraft through that hurricane, which is like what ICON is getting us. Okay. And so to kind of pull this all together, Bob and Dolores have introduced, why we want to study this region at all. We want to study this because the upper atmosphere and ionosphere, this is where most of the spacecraft flying currently are. It's where all the astronauts in orbit currently are. It's a region that interferes with radio signals, including GPS, that we all use every day now. And it can have profound impacts on things like the electrical power grid during major storms. But it is a region that's affected by multiple factors. There's changes in the sun, changes in particles in space, and also changes in Earth's weather system to do with, thunderstorms or large hurricanes and like. And we're now starting to put together the suite of observations that we need to start isolating each one of these and really understanding the system as a whole. Okay, I think we're ready for questions.
Great, thank you. We will now take questions from any reporters in the room. If there are any reporters who have questions, please raise your hand and state your name and affiliation. Are there any questions from reporters in the room? Great.
Pearl Tessler from the Exploratorium. This is a question for Dolores. I was wondering if you could fill in a little bit about the mechanism whereby nitric oxide cools the atmosphere.
Great question. Something I was thinking about. Oh, I missed that point. So nitric oxide is an interesting chemical. It is nitrogen and oxygen. That means it's not quite a balanced molecule. And if it gets excited or heated, which would occur during this time of disturbance, it actually starts to rotate and expand, contract. And when it does that and it goes back down to its ground state, it emits infrared radiation, like Scott was saying we're actually going to try and measure from ICON. So it's like a campfire cooling. And we see it cooling first in the high latitudes, and then the cooling expands. But the amazing thing is that we put energy in, we excite these molecules, it cools in the infrared, and it's nature reining itself in. First putting energy in and then going, oh, done too much here. How do I get rid of it? So it is infrared cooling like a campfire.
Hi. I think Dolores mentioned that this work is awaiting publication, or has it been accepted? I can't remember which. But can you let us know where it will be in print once it gets in the literature?
The technical article will be published in Space Weather. That's one of the AGU journals, and it is awaiting my finishing work here at AGU and getting on an airplane and going back with my red pen and fixing the things that the reviewers said, well, this wasn't quite so clear. So I think by end of month it will be out on the Space Weather website. It's not yet on the archive, right? It's too warm, not even warm off the press. It's warming up the presses.
Mike Carlowitz from the NASA Earth Observatory. I think this is for Dolores. I heard you say something about during certain storms, the energy is dissipating faster than it is coming in. Can you explain a little bit about what the effect of that is, or what effect does that have? Connected to that, you also mentioned shocked and non-shocked storms. Can you tell us what the difference is and how you see those?
Okay. So let me start with your second question first. If disturbances that come from the sun can come at the normal speed that the solar wind flows, which is supersonic, or can come even faster than that. And if they come faster, then the waves in the solar wind can help propagate it. Then it will form a shock, very much like a supersonic shock around an aircraft. And so we have been using other NASA assets, as have many scientists, for a long time. We look at the spacecraft that sits well ahead of Earth by about an hour in terms of typical solar wind travel time to determine which of the disturbances are coming faster than the normal solar wind propagation speed. And that in metric units is faster than 500 kilometers per second. So typically faster than about 1.5 million miles per hour. We go, oh, that's starting to come in pretty fast. Those are the systems that are known to rattle the magnetosphere. Well, now we know that they rattle the system in the ionosphere, thermosphere, and actually get it to, as I said, rein itself in. So it causes a very rapid heating. Within maybe 6 hours, we may see the temperature in the upper atmosphere spike by 400 degrees, which is a pretty healthy temperature increase. And in the event that I looked at, that's sort of the poster child event in 1967, in a few hours after that, we saw the temperature drop by 500 degrees. And that is called, in technical term, overcooling event. And when you are expecting the atmosphere to remain puffed up, but it contracts instead, as it would in an overcooling event, our models don't capture that. We are just now beginning with the 15 years of data provided by Time Saber and also with Department of Defense to have enough instances where we can investigate and say, that's what it's doing. So that's the new result. We can actually now capture it with a whole series of storms and say, in a general sense, here's what's going on.
I think you have another question here in the front.
Hi, I'm Rebecca Boyle. I'm a freelancer. I have a couple questions. I'm wondering what implications this has, if any, for climate models. If there's heating of the thermosphere and it's actually less warm than we thought, or there's rapid cooling happening, what has that play in climate models?
So one of the principal investigators for the Time Saber instrument, I believe he's here in the room, has recently shown that the background cooling, so there's actually a background cooling mechanism that exists. It's carbon dioxide. It does the same kind of thing. And that there is now additional cooling in the upper atmosphere more than we expected from the carbon dioxide. But the discussion and the research that I'm doing is not so much climate focused, because I'm looking at the nitric oxide. It's very much still storm focused. But we are tracking changes of all of the cooling gases in the upper atmosphere. But I'll let experts speak to that.
Are there any other questions from reporters in the room? Oh, we have another one up there.
Okay, I have another question. This maybe is for Scott. What type of monitoring will you be able to do in real time with these spacecraft? Would you be able to send alerts or, some kind of forecasting capability?
Yeah, so the two missions, ICON's in a low Earth orbit, and we'll be communicating with it about every 4 or 5 hours. So there's a bit of a latency to the data from that. But the Gold spacecraft is actually on a communications. The Gold instrument's on a communications spacecraft, so it will be downlinking in real time. So every photon they observe, they'll send a signal to the ground, and that data is going to the main institution is the University of Central Florida, but it's also being sent in real time to NOAA, who are going to use that for seeing how the upper atmosphere and ionosphere might respond to a solar flare, and the changes there can be very rapid. And so NOAA's really got that data with almost no latency, and is going to be using it in their alerts.
Are there any other questions in the room? Are there any questions on the chat? No? Okay, great. That concludes our press conference. Thank you. Next up at 11:30 will be a media availability with Thomas Zerbukin.